All right, so we just looked at the Choralski process and talked a little bit about embodied energy, and also talked a little bit about the irony that we currently using a lot of fossil fuels to get at the renewables, but hey, that's revolution for you. Okay, so this is probably the type of cell you're more familiar seeing, and what we're looking at are the intersection of individual crystal grains. And I talked briefly a second ago about the fact that if you let water freeze at a temperature close to 32 degrees, let it freeze slowly, you'll get relatively large crystals. And obviously the crystals are relatively large here, but it's polycrystalline. And the reason for the different colors is that the individual atomic lattices in there are actually at slightly different angles. Think about a chipboard or something where everything's sort of laying in at different angles, and you take a slice through it, and that's basically what we're seeing are different crystal grains. And so at these intersections, you're not going to have sort of the beautiful little picture that we saw here a second ago. You would have some kind of diagonal coming through here. Just think about the intersection of Mount Avenue where it intersects the diag streets in Missoula. You just got the potential for more accidents, and it's the same thing with the electrons flowing back and forth. There's just not as tidy a flow, and that's in general why the polycrystalline are not as efficient. Less expensive to make because you don't have to control the heat. You don't have to control the heat and the processing as well. You're still going to get crystals in there. They're not going to be perfectly aligned, but they still work. I did mention gallium arsenide. Let's take a look at where arsenic is. So here's gallium, here's arsenic, and here's germanium. So just like how phosphorus and boron sit on either side of silicon, gallium and arsenic sit on either side of germanium and perform a similar function. One thing, it says gallium arsenide cells have a band gap wider than silicon. It says one's close to the theoretical optimum for absorbing the energy in the terrestrial solar spectrum. So it's more or less tuned to what's coming out of the sun. So cells made from gallium arsenide are therefore more efficient from the monocrystalline silicon. It also makes them more applicable for concentrating arrays. So one thing to think about is, I don't know if they've got a concentrating arrays, that's in 3.6, but more or less you're using less material and just pumping more photons into the thing just with a lens. That's just more or less what a concentrating array is. All right, so box 3.3, band gaps and PV cell efficiency. Several things that add to inefficiency. I'm just going to read through the bullets here. It says, difficult to achieve as high an efficiency in mass-produced devices as in a laboratory. No secret there. Any mass production, you're always going to introduce some kind of defects. Laboratory cells are not glazed or encapsulated. So glazed just means you have glass on the outside to protect them from hail damage. You saw what kind of rough shape the ones outside my office are in. They just, they don't take much of a beating. PV module, they're inactive areas, so not the entire thing. So for example, right here on the solar car, there's a lot of inactive areas. You're just not getting any sunlight in there because of manufacturing constrictions. Small resistive losses in the wiring. diodes to protect cells from short circuiting. So all of the other components have a little bit of resistance. You're always getting a little bit of joule heating losses there. And then mismatches between cells of slightly different electrical characteristics if they're in series. And that's similar to, you can think of the cells, like one is going to act like an energy source and another one's going to act like an energy sink if they're not exactly at the same potential. Just like if you had, in electronics, you always kind of want to use batteries that are of the same date or freshness so that one battery isn't just kind of leaching off the other one. Similar thing with the PV cell. So that's what can lead to inefficiency. Let's just take a look at this 3.5. What may or may not be astonishing to you is that this car that is running at 60 miles per hour is doing so with 1.8 kilowatts. What is that? That's 2 horsepower. It's a 2 horsepower car doing 60. Might seem kind of weird, but check out the aerodynamics. The other thing is, the thing's got no gas tank. In the solar car that we built in 2012 for the Shell Eco Marathon, we were able to cross the finish line with about 75% of the energy that we left with. To win a race like this, you basically have to cross the finish line with as much energy as you left with. You don't just have a big battery bank and that's what gets you through. That all of your energy comes from the sun. So in these races, you're essentially finishing the race with more energy than you started, typically. 2 horsepower, they're running 3,000 kilometers with, it's just phenomenal when you look at the engineering there. 2 horsepower, they're doing 60 miles an hour. Obviously kind of flat. I don't know what the wind conditions were like, but pretty impressive engineering there. All right. Let's do one more section, and then we'll call it good. We'll finish up 3.5 and call it good. So 3.5, thin film PV, amorphous silicon, sometimes called A-SI. So not as ordered. The bonds are not as strong. Dangling bonds. So what they're mentioning here is that if you've got these dangling bonds out there, and that's basically, if we just look back here, anytime you don't have two of these junctions touching each other that well, they're just called dangling bonds. So to fix that, there's a little bit of silane gas pumped in, so that's SiH4, and a little bit of boron. You can think of it as like atomic caulking material, something that's just going to go in there and stick to whatever holes, I shouldn't say holes, but whatever dangling bonds happen to be ready to accept it. Because the hydrogen combines with the dangling bonds and basically seals it. So solar cells using an amorphous is a somewhat different form of junction. It's the PIN junction, and this is what they look like. So you still have your P-type, you still have your N-type, but then you've got this big chunk of amorphous silicon, and then a layer of silicon dioxide on the top. Cheaper to produce because you're not going through that big fancy Choralski process. It says that it absorbs light better. Not that surprising. Anytime you've got a lattice, you might imagine that a lot of reflection's going on. So it's They're darker. I mean, the amorphous silicon, you've probably seen them. You can even buy them for a couple bucks a watt, even at Home Depot. There's black. We've got a few in the lab over there, so they don't look as shiny. So obviously more absorption going on. And they tend to work a little bit better, if I'm not mistaken, in diffuse sunlight. And then there's multiple junction technology coming online to make them more efficient. But as of this writing, they're only up around 10%. Okay. Copper, indium, gallium, diselenide is another one. So here's your copper over here. Here is your indium. Indium is an interesting metal in that you can use it in applications where you need transparency. So the indium metal itself will, if combined properly, will be transparent. Therefore, you could use it in an application where you would have multiple chances to catch that electron, and that's more or less what's being shown here. Where and there's your transparent portion, and your gallium arsenide, and then subsequent chances at catching that triple junction, if you will. And it's in 3.6. I think, yeah, maybe we've got enough time. Yeah, let's just go ahead and finish this little section here, and then we'll call it good, assuming my battery holds out. Yeah, we'll make it. Okay. All right, so I mentioned concentrating cells. So if you have a relatively expensive semiconductor, one thing you can do is build an array that concentrates the sun's rays, and this is just sort of a parabolic concentrator, into a small, expensive P-type chunk of silicon. Here's another one. We mentioned that reflection is an issue, so one way to help out with that reflection issue is just make the surface rougher. You know, a roughened surface is just going to have more chances at collecting sunlight, more grabbing that photon. This is also, you might hear nanotechnology being kicked around. Here's an issue or an instance of nanotechnology where you've just got a single molecule of this titanium dioxide coating on the semiconductor. Flexible polymeric materials are mentioned, so it's not 100% essential that you use metals. Nanotechnology is also mentioned here as well. Quantum dots, I just had an interesting conversation yesterday with someone trying to understand quantum dots. And quantum dots are more or less just one big atom, if you will. It's like a chunk of material that might consist of maybe 1 million to 1 billion atoms. Sounds like a lot, but at the atomic scale, it's still tiny. It's on the order of nanometers in diameter, and they're constructed in such a way that they will emit and absorb radiation in the same way that a single atom would, but more in like a group basis, sort of more on a harmonic basis, if you will. Okay. Well, let's just stop there for today. That's enough on the physics. When we get into 3.7 and 3.8, we'll talk a little bit more about the technology and some of the practical applications. Those figures that we're seeing coming up here are some of the tests that we'll actually be doing in some of our other courses. We do that a lot in the practicum and in 243. Well, I mean, we've even got panels here. We can even test it out if we wanted to for this course.
All right, well, that's a pretty good dent into chapter 3. Yeah, I think we made it about halfway, so I think we'll be able to wrap up chapter 3 on Thursday. Let's see what else is coming down the pike. I am going to need you guys' help on Thursday dropping the wind turbine, because I want to get that over to Karis Park. I see problem set 1 is sitting there. Summary 1. Has everybody submitted summary 1?
Is it due? Yeah.
Oh, no, it's due, sorry, it's not. It's, yeah, yeah, it's not. Yeah, so any trouble at all in summary 1? I mean, I'd like to have that, turned in a week from today at the latest, but start, turning that in Thursday-ish, comment over the weekend, and then we'll look at it. We'll look at it a little bit together next week. We'll have most of next week to discuss that and some of the problem sets, and then plenty of time to get ready for exam 1 that just basically covers chapters 1 through 3. So we're on good pace for 102. All right, guys, thank you so much. We will see you Thursday. And yeah, I do want your help dropping that tower on Thursday too, please.